Okay, so here's a map that came from an app, a free app. Of course, you can choose to get the premium version to get rid of the commercials, the ads and stuff. Why is my phone not responding? At any rate, on this app, it's called Quake Feed, and it will show you where earthquakes happen and when they happen all around the world. You can also narrow it down to your region because there's so many going on all the time because we live on an active planet. Yeah, Quake Feed is the name of it if you're interested. And this is a screenshot from the app taken yesterday morning after the first little cluster of earthquakes. We were just looking at the app. So yesterday morning, there were 9 little earthquakes, the biggest of which was the 3.7 that you can see right here is the epicenter, the location of it. And this will tell me not only that, it will tell me how deep it was and stuff like that. So let's see, this 3.7 was 4.7 miles deep. And then there were a few other earthquakes right afterwards, like aftershocks, and they got a little shallower and shallower, and they were also smaller. Meanwhile, you might have felt the earthquake this morning around 5:30. It was a 3.2. It's not shown on this because this screenshot's from yesterday, but it was the opposite. The biggest quake was the smallest one, and then the biggest quake was the shallowest ones, and then the aftershocks were deeper and deeper. Um, so we have had about, I don't know, a dozen or 15 earthquakes. Here's the updated version since yesterday morning. So what's going on here? Well, remember the Earth's divided into plates and they move. They're carried by the convection currents in the mantle, right? We've talked about that so much already. And 2 of the major plates include the North American plate and the Pacific plate. And they're kind of going like this in relationship to one another. This is the Pacific plate, and the North American plate is kind of pushing against it. And that has made this huge earthquake fault system, the most famous of which is the San Andreas Fault. But just like, think about a wrinkle in fabric. It's not just one wrinkle, it ends up spreading out, right? Or think about glass breaking. It's not just one straight crack, it kind of splinters in multiple directions, doesn't it? And the splintering from this force is not just making earthquakes right here where the 2 plates directly meet, but it's making earthquakes over here where we are. And where we are, the earthquakes are not this side-by-side motion, which we call a strike-slip fault. Instead, it's a rising and falling motion. And there's 2 different kinds of rising motions. Ours is called a normal fault, which is best demonstrated by these blocks of cardboard. Each gap between a block represents a fault. So when we have earthquakes here at Tahoe, this is what happens over time, over millions of years. Lots of little quakes end up lifting the mountains on each side and dropping a valley in the middle. Now, it so happens that our valley also got dammed by volcanic activity. Mount Rose, Mount Pluto are old extinct volcanoes, but when they erupted millions of years ago, they dammed off this valley, trapping the water inside of it. And that's why we have Lake Tahoe, and that's one reason it's so deep. So a couple of years ago, I remember that in the newspaper there, they had measured that Slide Mountain, right here next to us, right, had grown an extra foot during that year from little earthquakes lifting it higher and higher. So Slide Mountain grew a foot during that 1 year, which would be actually a lot if you added up millions of years. There was another earthquake cluster that happened in the Tahoe region, North Tahoe region. I'm not sure that it was at the lake like these were. It seems to me that it was more up by Truckee, but there were many small earthquakes like this, and it lasted a month or more of frequent small earthquakes. So it's hard to say if this is the beginning of an earthquake cluster and it's going to continue for a month, or if it's done, maybe it's released all the pressure that had built up. That's what I would hope. Or if it's just preliminary and that there could be a big one coming in the future, in the near future. I hope that's not the case. And we talked about the possibility of tidal waves resulting from earthquakes at Tahoe, didn't we? Yes or no?
Talking about tsunamis.
Yes, tsunamis. Yeah, also known as a tidal wave. But yeah, so we think that this whole bay over here used to be land, and then there was an earthquake, and it all collapsed down into the lake. And in fact, we can see the debris on the bottom of the lake over here. And if that happened, it must have made a huge tidal wave, a huge tsunami that then hit the east shore, but then bounced back and hit the west shore and bounced back and forth. Each time it hits, it would lose some energy, right? So the first impact would be the worst, and then it would get less and less and less. So hopefully that's not going to happen, right? Hopefully this peninsula is not going to fall into the lake, because that's where I live. So I don't want my house to fall into the water. But it's hard to say, isn't it? My wife's been asking me, should we be getting earthquake insurance? I don't really have an answer right now. Earthquake insurance is not normally included in your home insurance policy. Fire is included, and flooding from your own plumbing is included. But if you're talking about flooding from outside, usually that's an extra policy, which most people around here don't need. But if you lived on the Truckee River, you might want it. Or if you lived on the ocean in Mississippi or Louisiana, where you could have hurricanes, you might want it, right? Same thing is true for earthquake insurance is a separate policy. So you have to pay more every year just in case an earthquake happens. And if it does happen, then you've got that money that they pay you to help rebuild, right? In the meantime, you're paying into them, and you don't even know if it's going to happen or not, right? Like we're paying our fire insurance, and we hope our houses don't burn down, but we're paying into it all the time just in case they do, right? Insurance is kind of a gambling sort of a thing. Okay, any questions about earthquakes before we go back to astronomy? Okay, so let's go back to where we left off. We were working on this, weren't we? Measuring distances in space, and there are these three main units that we use to measure distance. And if you haven't done it already, right now would be a great time for you to work on filling in this chart on page 5, because I'm going to name these three and give a brief description of them. Okay? So this is basically where we left off, was this chart on Friday, I think, huh? So the first distance that we use, the first unit that we use to measure distance is called an astronomical unit, or an AU. And an astronomical unit is defined as the distance from Earth to the Sun. Of course, there's a more formal definition than that, but that's the easy way to think about it. It's the distance from Earth to the Sun, and that is about 93 million miles. From the Earth to the Sun, 93 million miles. Sometimes when we're doing math, it's just easy to round off these numbers because they're so big, does it really matter? And I might just work with 100 million because 93 is pretty close to 100 anyway, right? At any rate, 93 million miles, Earth to the Sun.
How do we know that it's not
How do we know that it's 93 million? That's a very good question. Basically, we know how long it takes us to go around, right? And so if we can calculate that circumference, we could then get the radius from that, right? So through geometry, we can figure these things out. And then we have sent probes pretty close to the sun, although not into the sun. Well, not to like orbit the sun at a close distance. We haven't done that, but okay, here's our second measure of distance, a light year. So a light year is the distance that light travels in a year. You could also measure light seconds, light days, light months, light centuries, but we pretty much stick with light years. The distance that light travels in a year. Now the tricky one is the third one. A parsec is our third measurement of distance. And that is the distance to an object whose location would shift by 1 arc second in a year. The distance to an object whose location would shift by 1 arc second in a year. And didn't we do this the other day where we winked and saw how much our fingers jumped? I thought of another good demo. Put up both fingers at one time and line them up with each other and then wink and see which one jumps more. One should be close and one should be far. And if you line them up with both the same object with your right eye, for instance, then you shift to your left eye, you'll see that the close one jumps a lot further than the far one. And it's because this angle is different. If it's a close object, the angle, let's see, to like that letter E, for example. Let's look at that. So if we were going to measure to this object, much closer to us than that star, it would jump, its apparent location would jump from here to here during the year. It would move a lot more than what is shown, sorry about that. It would move a lot more in compared to the background stars than this yellow one that only moved that much. Does that make sense? The further it is away, the less it moves. The closer it is, the more it moves. And you can see that each of these units is going to be useful for measuring different sized objects. And that's part of the chart that we were looking at, right? So when we looked at this chart, by the way, here's where you should be able to get your miles, or by reading, you should be able to get your miles. Objects for which it's useful. Well, the astronomical unit is going to be useful for things inside the solar system. The light year is going to be good for things in the galaxy. And then a parsec is going to be good for things beyond the galaxy, further in the universe. Okay, so I'm going to let you work on finishing that chart if you didn't already on your own. but while we're talking together, I want to do some of this math with you. Okay? So, question number 1 at the bottom of page 5. Find the time it takes for sunlight to reach Earth. How long does the light released by the sun take to get here? Give your final answer in units that would mean something to a friend if you were talking about this. So you want to change the units into a meaningful measurement. Okay? So we start out, I just want to remind you that speed is distance over time. We usually think of speed as miles per hour, right? Well, what does that mean? Doesn't it mean miles divided by hours? The per is the divide part. Miles per hour. Miles divided by hours. Wait a minute, is miles a measurement of distance? Is hours a measurement of time? Right? So speed is distance over time. But what the question is asking for is for you to find the time. So this equation isn't going to help you until you rearrange it with algebra, right? And I'm not going to go over how to do that. Hopefully it's obvious. You multiply both sides by time, you divide both sides by speed, and we get this equation. Is that okay? So now we want the time is what we're looking for. By the way, this is what I mean by showing your work. When it says show your work, it's just asking you to write out the equation. You don't have to do the math by hand. You use a calculator for the actual math. But you show me what you did when I ask you to show your work. So time is equal to distance over speed, right? Well, up in this box, I've given you the distance and the speeds that we need, huh? So what's the distance that we're going to work with? 93 million miles divided by how fast by the speed? 186,000 miles per second. So now I'm going to have you do this by yourself. Get out your calculator. And you're going to put 93 million in there. You're going to divide that by 186,000. Hit the equal sign. And you're going to get an answer. So what I want you to do is write down your answer, which I'm not going to write down for you. But that was in seconds. And the reason I know that is because this was measured in miles per second. And to me, that number of seconds would be kind of weird to use in a conversation. It would be better to convert that into minutes. So when it asks you to describe this, give your final answer in a unit that would be meaningful to a friend, change this into minutes. So how do you change minutes into seconds into minutes? Yeah. How many seconds are in a minute? Divide. So you divide 93 million by 186,000, then you divide that answer by seconds, and now I think you're going to have a reasonable number when you're having a conversation with people. To say, oh, light takes this long to leave the sun. Excuse me. Light takes this long to arrive at Earth after it leaves the sun. Right? Does that make sense? So if the sun was to go out right now, would we know right now? Or would we find out in that much time? Okay, let's look at number 2. Mars is about 2 astronomical units from the Earth. Is that a distance, a time, or a speed? When I say Mars is 2 AU from the Earth, is that distance, time, or speed? That's distance. It takes 7 months for a rocket to reach Mars. Is that distance, time, or speed? Time, right? 7 months is a time. How fast is the rocket? Is the question asking for distance, time, or speed? How fast is the question, right? So what I'm looking for is speed. So I'm going to start by writing speed equals, and now I can go back to my speed equation up here, distance over time. How fast is the rocket? Show work. Give your final answer in miles per hour. So it's distance divided by time. And the distance was 2 AU divided by 7 months. Right? Well, we have to make some conversions here. We've got to change astronomical units to miles. So how many miles? 93 million times how many astronomical units? So we're going to have 2 times 93 million. And then that's going to be divided by 7 months. But wait, we want hours. So how do we change months to hours? Yeah, first we got to change it into days. And the number of days in a month varies, doesn't it? So we're just going to come to an agreement, and I hope you are okay with this, that we're going to call a month is going to be 30 days. Okay? So we're going to go 7 months times 30 days. But I'm not there yet because I have to get to hours. What else do I have to do? 7 months times 30 days, but I want it to be hours, so I also have to, how do I change days into months? Well, actually multiply by, or you could be dividing this, maybe you're thinking about it differently than I am. Okay, well, I don't really want to know that. I want to see the answer later. I want to show you how to get the answer and everybody else. But thanks. I will check it in a second, though. The last step, we have to take the months and turn that into days. So we multiply by 30, but we have to turn that into hours. So how many hours in a day? As I recall, there are 24 hours in a day, right? So this is what you need to do on your calculator. Multiply 2 times 93 million. And then there's 2 different approaches. One of them is you divide by 70, then divide by 30, then divide by 24. And that will give you your final answer. The other is you go 7 times 30 times 24, and then divide that into whatever 93 million times 2 was. And that should be miles per hour. Let's see what you got. This is oh, that's weird. 93 million, and it's 186,000 miles per second for 186 appears twice. Okay, so 186 million, right? 5 by 7, 5 by 3, divided by 24. That's what we're about. Okay. So you're going to do this math on your own instead of taking it out when I'm offering it? I guess that would. It's a big number. Go back. Okay, go ahead. Go 2 times 93. by 7. That's the 7 months. Yes. Divide by 30. That's the 30 days in a month. And now divide by 24, because that's the 24 hours in a day. You should get about that many miles per hour. Okay, and the last one of these math problems. Use the rocket speed that you calculated in question 2. So you're going to take the answer that you just figured out, which is many thousands of miles per hour, right? You're in the right ballpark. It was many thousands. You're going to use that speed to figure out how long it would take to get to the nearest star if the rocket was traveling at that speed the whole time. So your work, give your final answer in units that would be meaningful in a conversation. So, what is the nearest star? Did we talk about that? I believe we did, and I think it shows you right here in this chart where the nearest star is. So, the nearest star is 58,000 astronomical units away. Proxima Centauri is the nearest star. 58,000 AU away, or I might work with the light years, 4.25 light years away. Of course, you also have to change that into miles, don't you? This one also has to be changed into miles. Actually, since we already know that's 93 million miles, maybe that would be the easiest one to do, huh? So 58,000 and some AU to the nearest star. I'm going to write that down just so I remember. 58,000 AU to the nearest star. So on this one, what am I looking for? Am I looking for a distance, a time, or a speed? What's my final answer going to be here? Distance, a time, or a speed? What am I looking for? What's the question asked? You are looking to find out how long it would take. We want a time, don't we? So time is in that same equation. We just have to we can use the same thing here. Distance over speed, right? Distance over speed. What's the distance that I have to travel? Oh, I have to travel 58,000 AU, and I'm traveling at, I'm going to call it X thousand. I'm going to call it N thousand because I don't like the way that X looks. X N thousand. How about if I make a new number here? What I mean by N thousand is that you are using your answer from here, whatever that was, is this number, isn't it? $58,000 AUs divided by however many thousand MPH that was. Now, in order to do this, you're going to have to change that 58,000 AU into miles. Because you got to cancel out the miles in the miles per hour, huh? So how many miles in one astronomical unit? 58,000. What's that, Jess? Are you answering? How many miles in an AU? It's in the box up there. What was it? How far is Earth from the sun? It is. That's 1 AU. 93 million miles. Now we have it in miles instead of in AU. Then we divide it by however many thousand mph you had before, and that will give your answer in hours. Now that might not make much sense. There might be too many hours to even comprehend. So you might have to change your hours to days at the end. If you do, got to divide by 24 to make that happen, huh? And if that number is still too big to be meaningful, divide by the days in a year, divide by 365. So that we can get your final answer is probably going to be, let me see, it's going to be in days. Oh, it's even days is not going to be good enough. You're going to have to change it to years at the end. It's so far away. It's going to take you years to get there. So you're going to have a really big number to begin with. Huge number of hours. Convert that to days. Convert that. You can go straight from days to years. You can skip the months, huh? Because there's 365 days in a year. So divide by 24 to change hours into days. Then divide by 365 to change days into years. And that's probably a reasonable way to think about it. And then when you're finished with that, I want you to move on to page 6 and answer the questions on page 6. There's a graph that you're going to make, and then turn it in. You'll be done. So what was your in thousand? It was 36 million. Okay. Oh yeah, 58,000 AU. But you got 1.93 million. And what you get? Okay. Now divide by, yep. There we go. That's more like it. That's how many years it would take you to get there. To the nearest star. Yes. The nearest star only. Traveling at 36,000 miles an hour. Just do it in your calculator now. 58,000 times 93 million. Okay, this just means that there's 12 more zeros. Divided by 36,904. That's the number of hours it would take. When you're talking to somebody, 146 million hours, what does that mean? Okay? So let's divide by 24 hours in a day. Now that's how many days it would take, 6 million days. Does that have very much meaning? I don't know how long that is. So let's divide by 365 days in a year. That's how many years it would take you to the nearest star, traveling at 36,000 miles per hour. So could you get there yourself at that speed? Or would you like have to have some kind of rocket that had families on it that were living there for generations?
No, I just
Or you just teleport, you just do put some quantum tunnel in it.
you know, brains are not connected to the star, but
There it is. That's one reason that people would argue that the likelihood of seeing aliens is pretty low, because the distances are so huge. It would take so long for them to get here or us to go there that it's not really realistic, unless there's a way of traveling that we haven't discovered yet. Even traveling at the speed of light, it would take you 4.25 years to get to the nearest star. And we don't think anything can travel at the speed of light, except for light. On the first question, number 4, please pay attention to where the finger is located, right? One is close on the left, and the other finger is far away on the right. And as a result, the finger appears to move from one location to another, and you can see that it's jumping much further to the left and the right when it's closer. So that should help you answer number 4 if you think about that. We're really interested in the distance between the eyes and the finger. And the angle changes when it's closer or further. Just like the angle that we're looking at an object in space changes when the Earth is orbiting the sun. Like the left eye might be May 1st, which would make the right eye 6 months later, November 1st. And as we orbit the sun, the angle that we look at these things changes against the even further distant stars. Yeah. Okay, let me give you some hints on the graph. Very last thing you're gonna do here. So hopefully you were able to answer question 4. You figured out how to do the math on question 5 on your own. Question 6, you're gonna make a graph of these planets' distances. Okay? So whenever you make a graph, you need to ask yourself what goes on the x-axis across the bottom and what goes on the y-axis on the side. And for this data, you should choose to put the planet across the bottom on the x-axis, because that's really what's causing the changes in distance. So you're going to put the planet on the x-axis, and you're going to put the distance on the y-axis, right? Now, what I often see people do when they first do a graph for me is they say, oh, this first line is 0.387. The next line is 0.722. Don't do that. That's not correct. Every line should be equal to the same amount. In other words, you should count 1, 2, 3, 4, 5, not 1, 2, 5, 20, 800. That would distort your graph if you change the values of each line. So I think that excuse me, let me back up. What you need to do whenever choosing how much to make each square worth, each box on a graph, is you have to look at what your biggest number is. And for us, it's 30 astronomical units. So that means that your graph has to go from 0 at the bottom at least to 30 at the top, somewhere up here, 30. And you need to count evenly to get there. Now, it's important to communicate to the reader what that axis is. So when you have an axis here, and I'm just going to put it right on the edge because that's the easiest way. When you have an axis, you need to label what that is if it's numbers. So if you leave out the 0, that's something I'll be looking for, that you didn't leave out 0. And you have to get to at least 30. So do you want to count by tens? Well, that would squeeze everything at the bottom of the graph. That would be no good, huh? So I think you could probably count by ones. But does that mean you have to label every single line? Or could you just label the 5, 10, 20, 15, 20? Right? Does that make sense? I think you could do that. So this first one is 1, 2, 3, 4, 5 astronomical units would be here. 6, 7, 8, 9, 10. Does that look like I'm going to be able to get to 30 if I number like this? If I've only used up this much to get to 10, do you think I'll be able to get up to 30 eventually? To me, it looks like it's going to fit. So just keep going. I think you're fine to label every 5. And then are you going to draw bars, or is this going to be a line graph? And the way you make that decision is you ask yourself if the x-axis includes objects that are totally separate, then you would draw bars. And that would be correct for this one because Jupiter is not connected to Venus. On the other hand, if it was time across the bottom, 5 minutes is connected to 10 minutes. There's numbers in between. So in that case, you would use a line. But this one, you're going to do bars. You should put the bars in order, either from smallest to largest or largest to smallest. And here's 3 other things I'm going to look for when I grade this. 1, did you put a title telling me what this axis shows? What are those numbers on the side? You need a title on there. The same thing across the bottom. You need a title that tells me what this is down here. And then finally, you need a title at the top of the entire graph that tells the reader what the graph is showing. And I think I've mentioned this before, but first of all, it's obvious it's a graph. You don't need to include the word graph. A good scientific graph title is a full sentence, complete sentence. And the graph title includes the title for the X and the Y axis and tells how they're related to one another. So for hints on your X and Y axis titles and your overall title, I would look at the labels at the top of the table, of the data table. Those are things that you should have on the graph also. So if you do all that stuff, you'll get full credit for the graph. But I do look at them pretty closely, and I look to see, did you do this in the right place? Now, it looks to me like there might be some difficulty in measuring Mercury and Venus when you make your bars. So let's have a look even closer here. Mercury 0.38, Venus 0.77. That's kind of messy, so I'm going to get rid of that. Okay. So what I want you to notice, if this right here was 0 astronomical units, and this was 1 astronomical unit, then Mercury is less than a half of an astronomical unit. So your bar for Mercury should be very small, less than a half. Venus was 0.7. So that's more than a half, but less than 1 whole bar, right? And actually, there's a much better way to do this than drawing on it like I am. I'll show you that if you want to see. To make your bars be really nice, we should just draw rectangles. So for instance, for Mercury, I can draw a rectangle here that is like that big, less than a half. For Venus, I can draw a rectangle that's more than a half, but more than a half. More than a half, less than 1. Why I can't draw a rectangle? Oh, this is why. Between doing rectangles, go back and hit the typing icon and then click somewhere as if you were gonna type, but don't type anything. And that should reactivate your rectangle so that you can do that second one. Yeah, there we go. So there's my second one, nice rectangle. I can also fill these in. So if you right click on it, you click properties, and properties takes a minute. You go to fill color, and I'm going to fill it in with this red. Another thing that you can do that's quick and easy is you click on your rectangle, and then you copy and paste it. I like to use the keyboard shortcut, Control-C copies, and Command-C pastes. So you click on the rectangle, Control-C copies, Control-V pastes, and then I can just put that where I need it to be. That was Earth, 1 AU. Now, I'm making each of these planets be 2 boxes wide. Hopefully that'll fit. If it doesn't, I need to go back and adjust them so they're all equal. We don't want some be 1 box wide, others 2 boxes wide. That should be nice and evenly spaced You can also squeeze them completely together if you want to. I was spreading them apart, but you could squeeze them all together like this. That's also fine. You can have a different color for every planet if you want. That's okay. But don't forget to label which planet is which. You need a title saying that these are the planets. You also need labels saying that this is Mercury, Venus, Mars, as you go across the graph. They should all be labeled. You can also abbreviate, like I'm going to put M for Mercury, and then I'm going to put V for Venus. But if I do that, somewhere else I need to make a key that shows what those labels stand for. If you don't have room to write out the words, then you should make a key as well. Or you could number them. That would be another way to go. So I could come over here and show that M stood for Mercury, V for Venus, E stood for Earth, and I could show that this was my key. So let me know if you have any questions about this.